In the last video, we got as far in our quasi-historical coverage of the development of quantum mechanics as to present Bohr's model and see how that recovered Balmer's empirical fit for hydrogen. Now, the problem was that this was an ad hoc explanation and it didn't really have any kind of theoretical underpinnings. Bohr was simply saying when the right model is found, these features have to be present. So here we get to why Louis de Broglie was thinking about matter waves. He was trying to come up with a way to motivate why only certain orbits were stable. And he hit on the idea of standing waves. So if you remember, the way you make a standing wave with a string or something like that is you snap a wave down, it reflects back, that reflection interferes with what's going down the other way, they oscillate back and forth, and only for wavelengths that are certain multiples or actually certain multiples or fractions of the length of the string will you actually get a wave, and in any other case it just interferes itself out. And so de Broglie thought maybe we could do something similar for hydrogen, and so this is what he came up with. So we've got our proton sitting here, but now he's envisioning, let's say this is the n equals 1 state, that we have a standing matter wave. And I'm just going to apologize right now for how bad the art is going to be. So this is our standing matter wave around our proton. Now, why does it? So this distance here, all the way around, would be 1 de Broglie wavelength. Why couldn't it be half? Like we've seen, with a lot of situations in standing waves with strings. Well, that's simply because if it was a half a wave, let's say I had a crest here, if it was half a wave, then when I get around, that would be a trough. And that crest would interfere with that trough and it wouldn't work. So we can only have it so that in this kind of a situation where the wave is in a circular shape, in order to have a standing wave, it turns out to have to be integer multiples, or that we can fit an integer number of waves around. So the n equals 2 state, de Broglie is suggesting, would look something like this. And I'm just going to try to draw it like so. Yeah, that didn't work out so good. I'll just move the proton. There we go. And so the idea here is that much distance would be 1 de Broglie wavelength. So we fit 2 de Broglie waves around, and so forth. So you can say, well, all right then, the circumference of our allowed orbit would be 2 pi times the radius of that orbit. That would have to be equal to n, where n is an integer, times the de Broglie wavelength. Well, this would be equal to nh over p, or nh over mv. In case, it's just a quick reminder, whenever we're dealing with stuff like this with the hydrogen atom, the speeds of everything are low enough that we can get away with using non-relativistic expressions. Okay. So this is, so we have 2 pi, 2 pi Rn equals n h over mv. If I rearrange this around a little bit, I'll divide by 2 pi and multiply by mv. mvrn would be equal to nh over 2 pi. Well, this is the angular momentum, my nth state, and h over 2 pi is h bar. And so we get Bohr's quantization condition. So this is suggestive that, so de Broglie is onto something. Now, it turns out that there are technical details that he can't quite explain, but people are looking at it and saying, okay, at least he's onto something, and maybe this matter wave idea bears some more merit. And so eventually, it takes Erwin Schrödinger developing the Schrödinger equation, but then we can solve the Schrödinger equation. So I'm not going to rewrite the Schrödinger equation from earlier, but that is our key non-relativistic equation for quantum mechanics, which was based off of energy conservation. And I'll present some visualizations of the solutions, but I'm not about to solve it here. The key results that we get are that you can enumerate the solutions using quantum numbers. And it turns out we're going to need more than just the n that we were tossing around before. We're going to have a whole zoo of them. We will have the principal quantum number. That's our n. This dictates the total energy of the orbit. For hydrogen, solving the Schrödinger equation will give us that the energy that our allowed energy levels are minus 13.6 eV over n squared. And n here can run from 1 and onward. Okay. In addition to that, it turns out that you can have an orbital quantum number. This gets noted with L. And L, for any given solution, will run from 0 up until the principal quantum number minus 1. So if n is equal to 1, the only possible value of L is 0. If n is equal to 2, I can have 0 or 1. If n is equal to 3, I can have 0, 1, or 2. If n is equal to 6, I could have 0, 1, 2, 3, 4, 5, and so forth. It turns out that the total angular momentum of our electron orbit will be given by the square root of L plus 1 times h bar outside of the root. In addition to that, we will also have the orbital magnetic quantum number. This gets written as m or m sub l. I'll write m sub l here. M sub l is allowed to run from minus L to L in integer steps, and this will tell us the z component of the angular momentum. Now, basically what this is telling us is how the angle of this number compared to this number is telling us the angle. We can imagine this as the angle that our orbital plane would be tilted in if we take a semi-classical view of it. However, in a moment I'll present what the solutions look like, and we'll see that that holding on to a planetary view is probably not profitable. In addition, we've already run into electron spin in an earlier video. And so there is a spin quantum number. Technically, it has S, but for an electron, it's always 1/2. And so we tend not to even bother writing it down. But the total angular momentum of the electron is given by S plus, or whatever particle. It's given by S plus 1 h bar. So this is due to the orbital motion. This is due to this intrinsic spin property, whatever that is. And there is a spin magnetic quantum number. Usually written as M sub S. And just like this is again telling us kind of the angle at which we're leaning or whatever. Tells us the Z component of the spin. And again, it follows the same thing where M sub S can run from minus S to S in integer steps. Now, for an electron, there are only two possible values, negative 1/2 and plus 1/2 for this. Like I say, we don't even bother writing down the spin because that's the only value it can have. This usually gets called spin up, and this gets called spin down. And sometimes people will write like an up arrow or a down arrow rather than actually writing numbers. This basically, these last bits here, with the orbital magnetic quantum number, for instance, this is dictating some small shifts to the total energy in the presence of an external magnetic field. And the spin number is the same kind of idea. Alrighty. Now, to get some sense of what it really looks like, I have here a visualization of the solution for the n equals 1 state of the hydrogen atom. So this is solving the Schrödinger equation, and you can see that so this is the Schrödinger equation here. This is basically saying kinetic energy plus potential energy equals total energy. And we wind up getting the solution that Bohr says. And the way we can interpret this is a plot of how likely you are to detect the electron as a function of distance away from the proton. And it turns out to max out right at the Bohr radius. This actually works really well. But really, we kind of have to dispense with the idea of saying that we know how the electron is moving or whatever. It turns out that all we're ever really allowed to do in quantum mechanics is connect one observation to the next. So what this is telling me is the probability that if I look at a hydrogen atom, it's dictating the probability of where I would see the electron should I go looking for it. Some of the other states look a little more interesting. So this is principal quantum number 1, L equals 0, M sub L equals 0, which is the only possible set of angular momentum and orbital angular momentum and magnetic quantum numbers for this. If I go to 2, now I have more possibilities. This gets called 2s. If L is equal to 0, we call that S usually. in spectroscopic notation. And we can see that it's not quite, it turns out that overall, that the most probable place to find our electron now is at 5.2 Bohr radii out. Bohr was saying at 4, but you can see that there's another peak at just inside the Bohr radius. So you kind of put the two of those together, and Bohr wasn't totally wrong. So this is the 2s state, and this is looking like, the usual representation you see is like sort of like a basketball with a spherical shell around it, but these are continuous distributions. Except that right here at this spot right here, it turns out that at 2 Bohr radii out, there's no chance of the electron ever being exactly there if you go looking for it. That being said, the uncertainty principle means that if you look, you could have an error that includes that area. All right, but the electron could be literally anywhere. I mean, it could be in Cleveland right now. It could be wherever. It's just that the odds of it being really, really, really far away are very, 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 very low. And it's most likely to be found somewhere around here. And that's really all we can say. It's just when you look at it, that's the probability of where you're going to see it. And for us to pretend we know any more about what the electron is quote unquote really doing is sort of an act of hubris. Okay, but we can now have an L equals 1 solution. And this corresponds to the dumbbell solution. So you can see here, again, the most probable place we'll detect it is at 4 Bohr radii. So this is the L equals 1 solution for magnetic quantum number 0. Now, in a lot of chemistry books, we'll call this PZ, and they'll say it looks like a dumbbell aligned along the z-axis here. Pardon me, my z-axis in this simulation drifted a little bit, but you get the idea. And then they'll go and say that the other two are px and py, but that's not really quite right. If I go and take a look at the, so this is m sub l equals plus 1, and now I go and look down at it from above, what we see is it's actually donut shaped. And if we throw in something, a time-dependent thing known as the phase, we're not going to get into what that is, we can see in a certain sense that the m sub l equals 1 is a donut that's kind of going counterclockwise when viewed from above. And the m sub l equals minus 1 is a donut that's kind of going clockwise in some sense. This isn't really detecting motion, but it's talking about a thing called the phase. Now, was your chemistry teacher totally lying to you about the X and Y? And not quite. It turns out that in a molecular configuration, like what we're seeing here, you wind up getting, this one's aligned along the y-axis here, you wind up getting, let me turn the phase back off, you wind up getting a dumbbell kind of thing if you have a combination of the m sub l's minus 1 and the m sub l's plus 1. And with a different combination, a different way of combining it, you can get this to lie along the x-axis. And so it's more convenient when thinking about molecular bonding. But the actual solutions to the Schrödinger equation for 2p are actually, you have a dumbbell for m sub l equals 0, but then for plus and minus 1, you get the donuts. Okay, now, so what's going on with transitions. So let's go and take a look at, say, something like Lyman alpha. It turns out that what will happen with Lyman alpha is that when you are transitioning from, say, 2p, this would be the 2p state, to 1s, if we plot the electron cloud as a function of time, we see that this is sloshing up and down. And it turns out the frequency at which it's sloshing up and down is indeed the frequency of a Lyman alpha, in this case a photon. And similarly, if I go into the Balmer series, I'm transitioning from 3p to 2s, it's the same kind of thing, and we can see that the sloshing of the electron cloud is much slower. And that makes sense because in the visible, that's a longer wavelength than when it's in the ultraviolet. So longer wavelength is going to correspond to a lower frequency. And again, it is the frequency of this sloshing that we that corresponds to the frequency of the emitted photon. So as we're transitioning from 3 to 2, the electron cloud sloshes back and forth, or say if we go back to 2 to 1 like this, the electron cloud sloshes back and forth. This is basically making our little antenna to emit our electromagnetic wave, which will also say as we're emitting a photon. Because remember, the wave is really just dictating the probability of where we would see a photon if we go looking for it there. Now, I very carefully did 2p, which is where the orbital angular momentum quantum number is 1. And that's because let's see what happens if it's 2s. So in this case, both of these have an orbital angular momentum quantum number of 0. And look what's happening. It just kind of pulses. But so you'd think, well, gee, why, so I'm emitting light, right? No, it turns out not really. Because this bit right here is pulsing up when that bit pulses down. So this bit up here is going to make an electromagnetic wave orient one way. The bit pulsing in the opposite direction, the opposite part symmetrically, makes the electromagnetic wave point the other way. And they cancel. And you can pick this pairwise all the way across the thing as our electron cloud just keeps breathing in and out with time. So we wind up not emitting light in this case. This is an example of something called a selection rule, which we will summarize in a moment. It turns out that in order for us to actually see a photon, the angular momentum quantum number has to change by exactly 1. So for instance, if we go and look at the Balmer series in the visible, this is Balmer, this is Balmer alpha, this is Balmer alpha transitioning from 3p to 2s. It's also possible to transition from, if it's L equals 2, that gets called D, from 3D to 2P. And you can see that we are slowly sloshing back and forth, and we will emit the photon. But it turns out that we can't do 3p to 2s. If we do that, we end up with, if we look at it from more, this is a good angle here, you can see we get that same sort of oozing thing happening where it's totally symmetric. Whatever one part of the electron cloud does, there's always a matching part that's doing the exact same thing in the opposite direction. It makes the upside down of the electromagnetic wave and it cancels out. So we can't get any light coming out from this. Now, it's actually a little too strong to say you can't get light. There are channels by which you can get some emission anyway, but they are much lower probability, much less intense, and the transition and the time it takes for the transition to occur is much, much, much longer than the so-called allowed transitions. All right, so let's go ahead and summarize how our electron transitions work. So we'll go ahead and draw a term diagram where we can also keep straight our angular momentum levels. So this is going to be our principal quantum number. This is 1, then 2, 3, 4. And then I'm just going to jump right up to infinity. This is what we call the ionization limit. In other words, if I give more than that much energy, that's where the electron will leave forever. So then I'll note here L and the symbol. Let me move my little lines here. So this is L equals 0, gets called S. L equals 1 gets called P. L equals 2 gets called D. L equals 3 gets called F. And there's a whole story behind that. Basically, these actually stand for things. It stands for sharp, principal, diffuse, and fundamental. In the early days of looking at spectra, people were kind of trying to categorize the quality of spectral lines, and that's what they came up with. And then eventually that got attached to angular momentum levels. And honestly, this isn't even that good of a descriptor of the quality of the lines for many of the atoms, so it's just a thing. Anyway, we can go ahead and keep track of our energy while we're at it here. This is going to be minus 13.6 eV. This is also known as the ground state. This is our stable state here. N equals 2 will be at a quarter of that, so minus 3.4 eV. N equals 3 is at minus 1.51 eV. N equals 4 is at minus 0.085 eV, and so forth. Now, so this state here would just get read as 1s. This would be 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And so the thing is, remember here, L can only run from 0 to 1 less than the principal quantum number. So here, this is, so if this is 1, you can run from 0 to 0, so that's your only one. 2, I can run from 0 to 1, so that's why I get both S and P. 3, I can run 0, 1, 2, so that's why I get SPD. 4, I can run 0 to 3, so it's SPDF. So for an allowed transition, the L must change by exactly 1. Anything else will give you those breathing modes where you wind up not being able to make an electromagnetic wave. So for instance, let's start categorizing some of the allowed transitions. 2p to 1s is allowed. 3p to 2s is allowed. 3s to 2p is allowed. And 3d to 2p is allowed. All these have L changing by exactly 1. I can also say go from 3p to 1s. It's just a restriction on L. N can change by whatever it wants. And we can continue this process up. Maybe let's do it in a bit of a with the n equals 4 state. Yeah, let's do it in gray to try to reduce some of the clutter. So for instance, I could do 4s to 3p, that's allowed. 4p to 3s and 3d are both allowed. 4d to 3p is allowed. And 4f to 3d is allowed. And again, there's no restriction on the principal quantum number, so 4p to 2s is allowed. 4s to 2p is allowed. And 4p to 1s is also allowed. So these are allowed transitions. Now remember, forbidden transitions can occur, but they happen much more slowly and much less frequently. So when you're talking about what's going to give you the lines that you see in a spectrum, it's going to be these energy differences only. Alrighty, so then in the next video, we'll start to extend this out to multi-electron atoms and molecules and take it from there. So catch you over there.